Speaking of analysis, our next topic is Short Circuit Analyzer. It's another analyzer in a series of analyzers we've already developed and released with ETAP. The first analyzer we had released with ETAP was for load flow, followed by short arc flash, and then finally short circuit result analyzer. The purpose for a result analyzer is to essentially understand the results from multiple studies in one summarized table. So when you're trying to run various scenarios, whether they are for load flow or arc flash or short circuit, we obviously get multiple sets of results from these different cases or different scenarios. And the analyzer allows us to take these multiple cases, put them into a single view, and then compare. And in many cases, it also allows us to quickly identify deviations or alerts in the system and give us a summarized table that we can essentially copy and paste into our overall study report. So that's essentially the main concept of the short circuit result analyzer. In order to essentially demonstrate that, I'll cover a few basics first before we actually jump into the analyzer itself. Now, in order to prepare a scenario inside ETAP, we utilize what we call a multi-dimensional database, where you can take multiple data revisions. So these are essentially different engineering properties for the same electrical system. You can combine them with various configurations in the electrical network. So if I take an example of this large diagram that I have here, this is my normal system. If I consider a different configuration where one of the utilities is out of service, we can see that this utility and the transformer connected to it has been de-energized, whereas normally it's actually operating energized. So the configurations allow us to consider what's open, what's closed, which motors are spare or running continuously. Things of that nature can be packaged into a configuration. And then we have study cases, or essentially the study or solution parameters, where you can define various things like what fault standard do you want to use, what are the various parameters that control the outcome of the results based on different methodologies that have been given to us in these standards, and also control some of the basic things like which buses or nodes are being faulted or which ones are being analyzed in the electrical system. So when we combine engineering properties, configurations, and study cases together, we get what we call inside ETAP a unique scenario. So by clicking on the scenario wizard on my system toolbar on the left-hand side, I can launch this scenario wizard. I've gone ahead previously and created about 12 of these scenarios for my short circuit study. What the scenario wizard essentially gives me is a package that contains my revision, my configuration, what kind of study am I running, what sub-study or subtype of study do I want to run, which study case do I want to use, and obviously what is the output report that I will be writing my results into. So as we step through different scenarios, we can see that they are slightly different from each other, all 12 of them. And I can essentially select one of these cases at any point in time and press run and let the program update the output report, give me the alert views where we report the violations or summarize the violations in the system, as well as see the results directly on the single line diagram. So the study is done. Here's my alert view that's showing me my critical problems and marginal problems in the system. And the critical and marginal problems, again, are defined inside the study case. So anything that is past 100% of the device capability is thrown into the critical section. Any duty violations that are above 95% of the device capability, they are thrown into the marginal section. So essentially there's two different alert thresholds that you can include and control inside the program. And again, as I zoom into the diagram, we can see different results in the system. By the way, as I zoom out, this again highlights one of the features that John was mentioning previously when it comes to summarizing the layers on the one-line diagram. As I zoom out, we start seeing less and less detail of the one-line diagram because we are essentially using the theme manager to control at what zoom level different components are being shown or being hidden in the system, and this is also user configurable. So at this zoom level, my 3-winding transformer is summarized. I don't see the actual symbol anymore, but as I zoom in, I can see the details. So again, the scenario essentially is giving me the results on the one-line diagram. I can obviously look at my alert view and see my violations in the system. This is the traditional approach for doing the analysis. However, we want to summarize results from various scenarios. So these 12 scenarios that I have, I want to summarize all the results from all of these cases. So before I get to the summary, the next step I want to do is go to the study wizard and set up all the 12 cases that I want the program to run. So you can think of the study wizard as essentially a batch run, 1 through 12. They're all packaged inside the short circuit study. So when I press run, and I won't do it right now because it's a very large system and it will take a few minutes to run. I've already run this in the past. The program will essentially step through each scenario and start updating the output reports in each case. So obviously you can see the value of it right away. If I was to go inside this transformer and change any of the properties of this transformer, I obviously would have to rerun my entire study because it impacts my fault current contribution. Because it's so close to the source, it will impact every single component in the network. So by changing the property on one of the component, I can just quickly go back to my study wizard, press run, and get all my short circuit reports or load flow or motor starting or transient stability, all of them updated in one shot, and go back to my analysis and spend more time actually trying to find the problems and provide solutions or recommendations to for the electrical system. So I've already run all of these cases. In order for me to bring up the short circuit analyzer, you can actually access it from the short circuit toolbar right here. I'm currently utilizing an IEC short circuit scenario, therefore I'm seeing the IEC short circuit toolbar. If you were utilizing the ANSI standard, you will obviously see the ANSI short circuit toolbar. Regardless, the analyzer is for both ANSI and IEC. So when I click on it, the program gives me a selection for my standard. First of all, I can choose between ANSI or IEC reports. Now, in this particular system, it's a little bit unique because this system actually has a combination of IEC rated equipment as well as ANSI rated equipment. So we've had no choice. We run ANSI short circuit to compare the fault current contribution from the ANSI standard and compare it against the breakers that are ANSI rated breakers. And then we ran IEC short circuit to compare the IEC short circuit results against devices that are IEC rated. So it's a interesting example file that has both sets of equipment. So when I go to the standard selection, first of all, I'll start with ANSI standard. The next thing I have is a choice. Do you want to look at the 3-phase device duty or single phase? So I'm just going to stick to the 3-phase for now. And we can see that scenario 1, 8, and 9 are for ANSI, and if I switch over to IEC, the remainder are we're utilizing IEC standard for running the calculations. So first of all, we would like to see what's different in these studies that I've run. So I can just quickly select general, and that gives me an overall picture what's different in these 3 different scenarios that I created and I ran them So obviously my configuration is different. Because the configuration is different, the number of buses or components that were solved in each of these scenarios are slightly different. And we can see that the pre-fault voltage that was used is actually identical. It was 102% because we were trying to see what the maximum fault current levels are going to be. So the study case pretty much remained the same. In this case, the configuration changed. So with that approach, if I go to the device duty option, and device duty implies checking the short circuit rating against the capability or the device duty capability of the device, I have all of these different devices I can choose from: bus, breakers, fuses, and switches. Generator circuit breakers are split separately because there are additional factors or results that are calculated very specifically for generator circuit breakers due to the way the current decrements in a generator and the difference in the contact parting times and the response time of the breaker. So let me go back to bus real quick. So we have a list of buses. I've actually faulted all of them in this network. We can see some basic information about this bus. I've selected nominal kV. I can choose additional information like type and the pre-fault voltage that is used for that bus. The reason the pre-fault voltage would be different for different buses is in case if you were using load flow to determine what the pre-fault voltages are, in which case you would not have a fixed 102%. Each bus may have a different pre-fault level based on the load flow analysis. And actually we can do that very quickly. I have a case here which is ANSI operating, and inside this case I'm using pre-fault voltage, which is instead of fixed, it's actually using the magnitude from load flow. If I was to switch this to normal load flow configuration, run my load flow analysis, once the load flow completes in the system, and it just did on this network, I can go back to my short circuit analysis, select my operating configuration, ask the program to prompt me for a completely different report name. And I'm going to call this SC13, click OK. And what the program is doing now is using different pre-fault voltages for each of these different buses. So when we bring up the analyzer again, I'll see SC13 in my list as well. I can choose that as my reference. That's what I want to see now. Include the pre-fault voltages, and now you can see that they're no longer 102 for this specific report. They are 99 to 98%. They're more realistic based on the actual power flow in the system. So the information essentially allows you to see what input data was used for each of the components. The reference option allows you to pick and choose which is the main study that's being referenced in this table. So when the input data is being shown, where is that reference coming from? So in this case, I'm bringing reference from SC13. And then we can focus on the actual results themselves for our bus. So we have 4 different reports in the system. I can clearly see that my critical problems, which are any duty violations above 100%, are color-coded in red, so I can see those. And as I scroll through the table, I can also see that there are certain components that are marked in this magenta color. So any components that are exceeding 95% of the device duty capability. Now, let's say if you wanted to not even worry about the ones that are within the operating capability of the device or the interrupting capability of the device, you can just select this option, skip non-alerted devices, and in which case you can just focus on the components that are exceeding their device duty. So that's a much shorter list, and then we can spend more time actually analyzing this list and see why these components are exceeding the device duty in the system. You can also choose between different sets of results. Currently, I'm comparing all the symmetrical values in kiloamps. I can also switch over to asymmetrical, to the peak values, and you can see how quickly we just bring up the results from various reports and summarize them into this table. So it's a very fast table that can pull multiple scenario results and compare them side by side. Similarly, if I go to the high voltage breaker, we can also see the type of the breaker. So whether it's a 3-cycle, 5-cycle breaker, its interrupting capability, because this is an ANSI standard, contact parting time, and obviously which bus is connected to this circuit breaker. So again, you can turn on a lot of input data here. But the cool thing about the analyzer is this magic button right here called worst case. So if I have 4 different cases, I want to understand which case and what is the worst case magnitude that I get from that particular case. I just want one value. Give me the worst case condition that I need to compare against the breaker or bus capability in order to decide whether I need to upgrade this breaker or not. And if so, what value should I choose? In order to do that, you can just press the worst case option, and then very quickly all the various results are gone and replaced with one set of results. And we can see that the worst case for circuit breaker 3731 is 62 kiloamps. So any breaker rating that I want to pick for this breaker should be greater than 62 based on all the different cases that I have run in my system so far. And that worst case condition comes from scenario number 8. So as I scroll through, we can see that it just so happens that scenario 8 gives me the worst case fault current contribution for my ANSI rated devices. So now similarly, I can switch over to IEC. We have a number of additional reports here that are very specifically to IEC. Once again, I can go to my general section here and see that I have created all 3-phase device duty. They're using different configurations. And you can see that they're using different methods as well. IEC gives us method A through C for XORR adjustment for the peak kiloamps. So I'm essentially switching between different methods just to see which one actually yields the worst case fault current contribution. And all of them are utilizing the maximum C factor. So you can see the C factors here for different voltage levels, and they're all at 1.1, which is the standard IEC C factor for maximum fault current. So we'll switch over to device duty again. Same procedure applies. I have a selection of my device types, so I can switch between bus and breakers, fuses, and switches. I'll just stick to my high voltage breaker for now. You can again choose your input data just like ANSI for each of those devices. You can pick which result you want to compare. So IK double prime versus peak current versus the DC current, the short time withstand current. All of those can be easily pulled up from the reports and displayed. And once again, if you are selecting, let's say, the peak current, and we want to compare against the device peak capability, we are color coding the critical and marginal values and displaying them in this table. So once again, I can click on my worst case condition, and I can see that for all of these breakers, their size or rating must be greater than 90 kiloamps peak. So it kind of helps me or assists me in evaluating or picking the best size for the circuit breaker. But here you can see that these values were mostly generated from scenario number 7, but then there were certain cases where a different scenario resulted in the worst case value. So in a case where the tie breaker was closed, it so turned out that these two breakers had higher duty than if the tie was actually open in the system. Some minor options here, just for the sake of understanding. You can also choose to switch the values between kiloamps and amps. So very quick toggle button here. And if you decide to see the voltage in volts instead of kilovolts, you can also toggle from here directly. Now let's say I wanted to take this data into Excel because I want to do different types of additional analysis through Excel, or color code things in a different manner. You can just select this entire table, Control C or copy this table. I'll bring up an empty Excel workbook here, and I can just simply paste that information into the system. And then through Excel, you have a choice. You can also do things like conditional formatting, where you can select things that are greater than a certain value. Let's say anything greater than 100, mark it differently, and this will give you exactly the same type of table that we see inside ETAP. So 180 was color coded, and that's essentially what we see right here. So you can also change your formatting criteria by taking it into Excel or doing additional manipulation of the data. So in summary, the short circuit result analyzer utilizes multiple reports and compares those multiple reports into a single view. You can obviously expand on the usage of the analyzer by combining it with the scenario or the study wizards. So you can package each scenario into a inside the scenario wizard. You can then take multiple scenarios and package them inside a study wizard and automate the process of running the study, so you can spend more time actually doing the comparison or the analysis of the study. And once again, the short circuit result analyzer is very similar to the load flow and arc flash analyzer, where we're essentially taking voltage drops and losses for load flow and comparing them across multiple studies. For arc flash, we are comparing the incident energy and the fault, arc flash energy levels, and reporting the worst case for you. And once again, this short circuit analyzer will be released as part of ETAP 14. It's a very nice capability added to the short circuit module, and it is available as part of the short circuit module itself. So if you want the short circuit analyzer and you don't have short circuit, again, you may contact us at sales@etap.com, and we'll be more than happy to add that to your configuration.